Hello and welcome to problem set number 10. Our topic today is bond polarity and polar versus nonpolar molecules. If you have not already done so, I do highly recommend that you pause here and take a moment to go print off the worksheet that I will be covering today. And with that said, let's go ahead and get started. Okay, number 1. Use an electronegativity chart such as the one found on slide 3 of tutorial notes for bond polarity and polar versus nonpolar molecules to calculate the electronegativity difference for the following bonds. Label each bond as polar or nonpolar. For any polar bonds, indicate the direction of electron pull with the partial positive and partial negative signs. All right, so we are definitely going to need our electronegativity chart. And so I'm going to hang up the chart that I provided in the tutorial notes on slide 3. You probably cannot see that through the camera, but I'm hopeful that you either have that in front of you printed out, or you have one from your textbook, or you can also be looking online at an electronegativity chart. All right, so we're going to need that to do A through G here. So first we're going to calculate the change in electron negativity for a carbon-carbon bond. And you might remember from tutorial 10 that anytime you are calculating the change in electron negativity for the same two atoms sharing electrons in a bond, the delta En is going to come out to be 0. But let's go ahead and calculate it anyway. Even if you remember that, it's still good practice to go ahead and look at the chart, look up the electronegativity value for carbon. It's 2.5, so this is for a carbon-carbon bond. So 2.5 minus 2.5, the delta En is 0. And when the delta En is anywhere below 0.5, we're talking about a nonpolar bond, nonpolar covalent bond. So that means that the electron density here is being shared evenly, and we don't have any partial positive or partial negative charge buildup. So let's go on to B, a nitrogen-hydrogen bond. Okay, so we're going to look up the electronegativity of nitrogen. It is 3.0. For hydrogen, it is 2.1. So we've got 3.0 minus 2.1, because remember, you're always subtracting the lower electron negativity from the higher one. You're always going to come out with a number that is positive, 0 or above, never a negative here. So we've got a difference of 0.9, and this falls in the polar covalent range. Remember that anything between 0.5 and 1.9 is considered uneven electron sharing in a covalent bond. We call that a polar covalent bond. So now we do want to indicate where the partial negative and partial positive charge buildup is going to be. I'm going to go ahead and do that in the green pen. Okay, so between nitrogen and hydrogen, nitrogen had an electronegativity of 3.0, hydrogen was only 2.1. That means that your nitrogen is better at drawing the electrons that are being shared here toward itself, which means that nitrogen is going to end up with more of the electron density, giving it the partial negative charge, leaving hydrogen with a partial positive charge. Okay, C. A carbon, carbon-bromine bond. The change in electron negativity for a carbon-bromine bond, let's go to our electronegativity chart. Carbon is 2.5, bromine is 2.8, so it's going to be 2.8, the higher value, minus the 2.5, the lower value. That's only a difference of 0.3. That is less than 0.5, which makes it a nonpolar covalent bond. Okay, so it might be helpful, y'all, right here, just real quick before we go on to D, that 0.5, remember that's the cutoff between nonpolar and polar, and then that 2.0 was a cutoff between polar and ionic. So anything that was less than 0.5, remember that that's a nonpolar covalent bond. Okay, anything that is 0.5 to 1.9, remember that that is a polar covalent bond. And anything that is 2.0 or higher, so greater than or equal to 2.0, is an ionic bond. So that might be helpful to have that over here. Do that. Okay, as we go through these problems. All right, so a nonpolar covalent bond for C, which means no partial positive, no partial negative charge buildup. So we're going to move on to D. D is a carbon-hydrogen bond. So the delta En for a carbon-hydrogen bond is going to be 2.5 for carbon minus the 2.1 for the hydrogen. So 2.5 minus 2.1 gives us 0.4, and that is in the nonpolar covalent range. So this is a nonpolar covalent bond. So again, no partial positive, no partial negative charge buildup. The electron density between the carbon and hydrogen is being shared pretty much evenly. All right, let's squeak E in here, and then we'll erase for F and G. So E is silicon and bromine. So the delta En, the change in electron negativity here. For bromine, it's 2.8. For silicon, it is 1.8. So 2.8 minus 1.8, the delta En is 1.0. That is in the polar covalent range. So this is a polar covalent bond, which means that there is partial positive and partial negative charge buildup. Let's indicate that buildup in green. Okay, so bromine had the higher electronegativity value of 2.8. Silicon was lower at 1.8. So that means that the bromine is winning this tug of war here for the electron density. And remember that electrons are negatively charged. So bromine having more of the electron density has more of the negative charge, so partial negative, leaving your silicon partial positive. Okay, I'm going to erase A through E so that we can go on and finish off number 1, F and G. Okay, F. It's an iodine bromine bond. So to calculate the change in electron negativity, you've got to look at the chart. Iodine is 2.5. Bromine is 2.8. So we've got 2.8 minus 2.5. We've got a change in electron negativity of only 0.3. That is in the nonpolar covalent range. So it's a nonpolar covalent bond. So no partial positive and partial negative charge buildup. The electrons are being shared evenly between those two atoms. Last but not least here, G, we've got a sulfur oxygen bond. Okay, so the electronegativity value for oxygen is 3.5. For sulfur, it is 2.5. So we've got a difference of 3.5 minus 2.5, or 1.0. That falls in the polar covalent range. So this is a polar covalent bond. That means we do need to indicate the partial positive and partial negative charge buildup here. So I'm going to go to the green pen. And remember, it was the oxygen with the higher electronegativity value of 3.5. So the oxygen is going to be winning this tug of war for these two electrons. It's going to have a little bit more of the electron density, giving it a partial negative charge, leaving our sulfur, which is less electronegative, with a partial positive charge, a little bit less of that electron density. All right, let's erase here and go on to number 2. Okay, number 2. Assume all bonds in these hypothetical molecules are polar with a dipole of 0.9. Which molecules would you expect to be polar? A molecule with a linear molecular geometry. Okay, so linear, that means that our central atom has bonds to 2 other atoms at 180 degrees apart in 3-dimensional space. Okay, so if we have equal magnitude for the delta ENs, we know they're both 0.9. So these are polar bonds, but a linear molecule, meaning that they're equal in magnitude and opposing in direction, we know that they are going to cancel out. And overall, the molecule is going to be a great example of a molecule with polar bonds that cancel out, leaving a non-polar molecule. Just like the example that I gave in the tutorial number 10, which was carbon dioxide, where we had polar bonds, linear molecule, they canceled out, and the molecule overall was nonpolar. Okay. All right, let's go on to B. A molecule with a bent molecular geometry. So now we're talking about a molecule where the central atom is bound to 2 other atoms, but they're not 180 degrees apart. There's either one lone pair here, creating a bond angle of 120, or there could be 2 lone pairs, creating a bond angle of 109.5. Okay, either way, these are bent molecular geometry. So we know that we have polar bonds. Doesn't matter which one you're looking at. We'll just pick this one here. We know we have polar bonds. Okay, they are not going to be equal and opposite in direction like the linear molecule. They're angled down into the bent geometry, and so they're not going to cancel out. So you are going to have a polar molecule. So this is a great example of a molecule with polar bonds that are not equal and opposite in direction and therefore do not cancel out, leaving the molecule polar overall. Okay. All right, C. A molecule with 2 bonding pairs of electrons and 1 lone pair of electrons on the central atom. So 2 bonding pairs. I'm keeping these real generic because we're not actually talking about a specific molecule. We don't know what this is. So 2 bonding pairs, so probably a double bond and a single bond, and then a lone pair of electrons here. Okay, so that's going to be same thing as what we talked about up here. It's a trigonal planar electron pair geometry, but because you've got a lone pair, the molecular geometry is not the same as the electron pair geometry. It's going to be a bent geometry instead, and so we're going to see that those 2 polar bonds do not cancel out like they would if the molecule were linear, but instead add together and create a polar molecule. Okay, last but not least, for number 2, D. I think we can squeeze it in here. A molecule with a tetrahedral molecular geometry. Okay, so tetrahedral molecular geometry, that means that your central atom has 4 bonds, no lone pairs. I'm going to make this one coming out of the plane and this one going into the plane of our chalkboard, because remember, in a tetrahedral geometry, all of your bond angles are going to be 109.5 degrees. That goes for all of them. So all of these. Okay. So you might remember in tutorial 10 that we said anytime you have polar bonds that are equal in magnitude, like they are here, they're all a delta En of 0.9, so is given in the problem, okay? Equal in magnitude and opposing in direction, they will cancel each other out and the molecule will end up being nonpolar. And then we further said that this is going to happen anytime you have a molecular geometry where there are no lone pairs on the central atom. So that's going to be your linear molecular geometries, your trigonal planar molecular geometries, and your tetrahedral molecular geometries. So this is definitely going to be a nonpolar molecule. Now, with that said, that's kind of messy there. Okay, with that said, I want to talk about that just a little bit more. The way I like to think of the tetrahedral being equal in magnitude and opposite in direction and therefore canceling out to 0 is that let me redraw this up here nice and big. Okay. I think of I'm just redrawing this nice and big up here, nice and fresh drawing. I like to think of the molecule as being split in half. Okay. And on this side of the molecule, I have, in this case, a magnitude 0.9 and another magnitude 0.9 at an angle of 109.5 degrees in three-dimensional space. Okay. What do I have on the other side of the molecule? I have the same exact thing. I have a bond with a magnitude of 0.9, a delta En of 0.9, and another with 0.9. We actually don't know which is more electronegative because this is a hypothetical molecule, but just kind of ignore that for now. And they're at an angle of 109.5 from one another. So the sum of these two forces at 109.5 degrees in space is going to be the same as the sum of these two forces, which are the same magnitude and also at 109.5 degrees apart in space. And so really it just becomes the same thing as the linear, where we were looking at equal in magnitude and opposing in direction, and they canceled out. Same idea here. These two forces at 109.5 degrees apart are equal to the sum of these two forces, also at 109.5 degrees apart. So they cancel out, creating a nonpolar molecule. So I'm going to put a big X there. It's getting really messy. Sorry about that. But I hope that made sense. All right. You don't really even have to think through it so much every single time you do this on a test. If you remember that as long as they're equal in magnitude, in this case they're all 0.9, and opposing in direction, which is anytime you have linear, trigonal planar, or tetrahedral, it's going to cancel out. It's going to be nonpolar. Okay. All right, let's go ahead and erase number 2 and go on to number 3. All right, number 3. Draw Lewis structures for the following molecules and determine if the molecules are polar or nonpolar. A through E. So it's going to take a little while. All right, A is nitrogen trichloride in Cl3. All right, so remember from tutorial 10 that we said anytime we have a molecule that's larger than just 2 atoms, we really need to do 3 things. We need to draw Lewis structure, we need to analyze the molecular geometry to see what it looks like really in 3-dimensional space, not just 2 dimensions like Lewis structure shows. And number 3 thing we need to do is analyze the individual bonds for polarity, the delta En. All right, and then we'll be able to figure out if the molecule as a whole is polar or nonpolar. So let's go ahead and start with the Lewis structure here. We label this, we're going to do the Lewis structure first. And there are 5 steps to getting your Lewis structure. First thing you want to do is add up all your valence electrons. So nitrogen is going to have 5 because it's a group 5 nonmetal, and each chlorine is going to bring 7, but there are 3 of them, so 7 times 3, that's 21, plus the 5 from the nitrogen. We've got 26 valence electrons. Okay, that's step number 1 in drawing a Lewis structure. Step number 2, single bond connectivity to show how the atoms are connected. Nitrogen's going to be in the center. We can conclude that for a couple of reasons. One, we know that when there's only one of an atom, it's typically because it's the central atom. We also know that your halogens, your group 7 halogens, like to form just one bond and keep 3 lone pairs to themselves. That would mean that they're typically going to be terminal, kind of like hydrogen. Okay, so I'm going to put them on the outside. Step number 3, complete your octet on your outermost atoms. So I'm going to go ahead and complete my octet for all the chlorines. Nitrogen is in the center, not the outer. So they've each got 2. They need 8. So 2, 4, 6, 2, 4, 6, 2, 4, and 6. Brings all of them to a total of 8. Step number 4, any leftover electrons go on the central atom, nitrogen. We've used 8, 8, and 8. We've used 24, and we have 26. So we've got 2 left over, so we're going to go ahead and put them on nitrogen. Okay, and step number 5, if octet is still not satisfied on your central atom, start forming double or triple bonds as needed. Nitrogen has 2, 4, 6, 8. 3 of them are in these single bonds, or excuse me, 6, 2, 4, 6 are in these single bonds, and then another 2 as a lone pair. So Na, not applicable. We don't need to change anything for number 5. This is our final Lewis structure for nitrogen trichloride. All right, now let's figure out the molecular geometry. We've got 1, 2, 3, 4. 4 charge clouds. 4 regions of space with electron density that are going to repel maximum distance apart in 3-dimensional space. And for 4 charge clouds, that's always going to be 109.5 degrees apart. So let's redraw this up here. This bond and this lone pair are going to be 109.5 degrees apart in 3-dimensional space. Same thing for this chlorine, so I'm going to indicate it coming out at us. And this final chlorine, so I'm going to indicate it going away from us. Now that's the electron pair geometry. The molecular geometry just looks at the atoms that are covalently bound together, not the lone pair. The lone pair does dictate that they are closer than you would expect. If there was no lone pair there, these could be 120 degrees apart instead of 109. So the lone pair is important, so the electron pair geometry is important, but the molecular geometry is just looking at this shape, which is the shape of a little pyramid. So this is pyramidal. A pyramidal molecular geometry. All right, now we're ready to analyze the change in electron negativity for a nitrogen-chlorine bond. Notice that they're all nitrogen-chlorine bonds, so we just need to calculate it once. It's going to be the same for each of them. Let's go ahead and put up our electronegativity chart. Chlorine is 3.0. Nitrogen is also 3.0. So we've got 3.0 minus 3.0, 0, nonpolar covalent bond. So that means that the electrons between this nitrogen and chlorine are being shared evenly. The electrons here shared evenly, and here shared evenly. No partial positive, no partial negative charge buildup. All nonpolar bonds. It must be a nonpolar molecule. So I'm going to write here, nonpolar bonds and nonpolar molecule. Okay, there's our final answer. All right. It's going to take a while. We've got B through E to go. So let's go ahead and erase here and go on to B. Okay, B, water, H2O. And to make these go a little bit faster, I'm not going to go ahead and do the 5 rules for your Lewis structures for B through E, because I don't want this to get unreasonable with the time, okay? So we're trying to figure out if water is a polar or a non-polar molecule. We're going to go through the 3 steps of drawing the Lewis structure, analyzing for the molecular geometry, and then analyzing the individual bond polarity, the delta ENs. All right, so my Lewis structure. And if you need to go through the 5 rules, do so. I just want to speed this up a little bit. And Lewis structure is not the focus of this tutorial, or this problem set. All right, so there's my Lewis structure for water. Now for my molecular geometry. We have 4 charge clouds. They're going to repel maximum distance apart in 3-dimensional space. That's going to be 109.5 degrees. So I'm going to redraw this. And attempt to show a bond angle here of 109.5 instead of what looked to be 180 over here, which is wrong. Okay. Now the molecular geometry is not going to be the same as the electron pair geometry, which is tetrahedral because it's 4 charge clouds. The molecular geometry just looks at the shape of the molecule, the atoms that are bound together here. So we get a molecular geometry that is bent. Okay, so now we're ready to calculate our change in electron negativity. We're going to calculate it for an OH bond. Oxygen is 3.5, hydrogen is 2.1, so we've got the difference between 3.5 and 2.1. Is it 3.5? Yeah, okay. And we get 1.4. That is definitely in the polar covalent range, so these bonds are polar covalent. We're going to have partial positive and partial negative charge buildup within this molecule. The oxygen is more electronegative, so it is going to be partial negative in charge, leaving your hydrogens with less electron density, causing them to be partial positive in charge. Now, because of the shape of the molecule, it is not linear, which would cause them to cancel. It is bent. We actually get some adding together for an overall partial negative charge on the oxygen side of the molecule. This is a great example of a molecule that has polar bonds that are not equal and opposing in direction and therefore do not cancel out, leaving it a polar molecule. So I'm going to write down here polar bonds and a polar molecule. Okay. All right, let's go on to C. Okay, C is phosphorus trichloride. And again, I'm going to just quickly draw a Lewis structure. But if you need practice with that, do go through those 5 rules to get your drawing. Okay, so we're going to have a lone pair there. And then the molecular geometry. All right, geo for geometry. We've got it drawn here as if we've got 90-degree bond angles, but that's not going to be the case. You've got 4 charge clouds. Maximum distance apart then is going to be 109.5 degrees in 3-dimensional space. So we're going to have a bond angle here of 109.5, not 90. That means if these are all in the plane of the whiteboard, this chlorine would be coming out, and this chlorine would be going into the plane of the whiteboard, and all of these angles are going to be 109.5 degrees. So our electron pair geometry, which has accounts for 4 charge clouds, is tetrahedral, but because you've got a lone pair on the central atom, your molecular geometry is not going to be tetrahedral. It is going to be pyramidal. Okay, now let's analyze our change in electron negativity for a phosphorus-chlorine bond, the delta En for a PCl bond. So we've got phosphorus 2.1, we've got chlorine 3.0. So 3.0 minus 2.1 gives us 0.9. Remember that that is in the polar covalent range. So this is a polar covalent bond. That means that we have partial positive and partial negative charge buildup within this molecule. And because our chlorine is the more electronegative, it's better at pulling the electron density to itself. The chlorines are all going to have partial negative charge, leaving our phosphorus partial positive in charge. Now, because we have a lone pair up here, throwing off the opposing forces, these are not going to be equal and opposite in direction. We're going to overall have some uneven electron distribution in this molecule, leaving it a polar molecule. So another great example of a molecule that contains polar bonds and they do not cancel out, so it is a polar molecule as well. All right, let's go on to D. Okay, D, sulfur dioxide. Lewis structure. Again, I'm just going to do it fast. You can go through the 5 rules if you need to for extra practice. Okay, molecular geometry. I'll just write GEO here. We've got 1, 2, 3. We've got 3 charge clouds. So maximum distance apart in 3-dimensional space is going to be 120 degrees. So I'm going to redraw this to try to show that angle of 120 degrees here. Okay. And here as well, but I'll just label one of them. All right. So we can see that this is not going to be linear like the Lewis structure kind of indicates. It's going to have an electron pair geometry that is trigonal planar and a molecular geometry, because of the lone pairs, that is bent. So the molecular geometry is bent, not linear. That is very important here. Now we're ready to calculate the change in electron negativity for a sulfur-oxygen bond. Oxygen is 3.5, sulfur is 2.5, so the difference is going to be 1.0. That is a polar covalent bond. With the partial negative charge buildup on the more electronegative atom, which is your oxygen, so partial negative charge buildup on the oxygen, leaving your sulfur partial positively charged. Now, if this were a linear molecule, those would be opposing and they would cancel out to 0, but it's not. It's bent, and that's why that Lewis structure and molecular geometry are so important here. If you cannot figure out the Lewis structure and the molecular geometry, you might miss the fact that this molecule is bent, which is why these polar bonds do not cancel out, and we have not just polar bonds, but also a polar molecule. So I'm going to write here polar bonds and a polar molecule for sulfur dioxide. Okay. All right, last but not least, E. Okay, E, carbon tetrachloride. Again, just a quick Lewis structure. And if you need the practice, make sure that you slow down and go through the 5 steps here, but I'll go ahead and just write the final Lewis structure. And my molecular geometry is going to be tetrahedral based on my 4 charge clouds, all of which are bonding electrons, no lone pair of electrons. So molecular geometry is tetrahedral. So I'm going to go ahead and redraw this to show the proper bond angle here, which is not a 90-degree angle, but remember 4 charge clouds will always repel 109.5 degrees apart in 3-dimensional space. So I'm going to go ahead and indicate that bond angle here with these 3 atoms in the plane of the whiteboard, which means this chlorine is coming out of the plane of the whiteboard toward you, and our final chlorine is going into the plane of the whiteboard, going away from you. So go ahead and label, we'll just label this one here, but all of these bonds would be 109.5 degree bond angles. All right, so you might already know just from looking at the molecular geometry, knowing that it's tetrahedral and that all of these bonds are equivalent, meaning they're going to have the same delta En, the molecule's going to have to end up being nonpolar, right? Because they're going to be equal in magnitude and they're going to be opposing in direction. That's always going to be the case for your linear, trigonoplanar, and your tetrahedral, so long as you're talking about equal magnitudes, equal delta Ens. But let's go ahead and calculate the delta En anyway, just for practice. So the change in electron negativity for a carbon-chlorine bond. Chlorine is 3.0, carbon is 2.5. So the delta En for a carbon-chlorine bond is 0.5, and that is in the polar covalent range. Just barely, but it is polar covalent. So there will be some partial positive and partial negative charge buildup. The more electronegative atom is chlorine, so that means that chlorine is winning the tug of war for these shared electrons here in this bond. It's going to have more of the electron density, and chlorine's going to have the partial negative charge. That goes for all of these bonds, because they are all carbon-chlorine bonds, and that leaves our carbon partial positive. But once again, equal in magnitude and opposing in direction. And so they're going to cancel out, and overall the molecule is going to be nonpolar. So I'll write here equal in magnitude and opposing in direction. Therefore, a nonpolar molecule. Okay. All right, so this concludes our problem set number 10. I hope you will consider tuning in to tutorial number 11. Thank you.